Welcome to Data Science with EJD. In this next set of videos, we'll be looking at validation and tuning in supervised learning, of course, which is under machine learning. Don't forget, we're talking about data science. Machine learning comes under that. And under machine learning, we have supervised, unsupervised, and reinforcement learning. And under supervised learning, we've been considering supervised learning all along, and we see that there are two main aspects of supervised learning where we have classification algorithms and regression algorithms. So in the process, also we see that there are certain metrics that we use, to measure the performance of those algorithms. So, going forward, we are looking at validation and tuning in supervised learning. In this particular video, our focus is on train test split and cross validation. Of course, in every machine learning algorithm, you have your data set, right? And it's important to split the data set into two, that you have a trained set and a test set. So the trained set is what you use to train the model, and then the test set is what you use to evaluate the model to see how well it does. Okay, and of course, we've used that all along. Here we are looking at it a bit more closely. So the learning objective is to validate machine learning models properly using structured techniques such as train test split and k-fold cross-validation, ensuring that the model generalizes well to unseen data. So our goal in machine learning is after training your model, you want to be sure that you get if the model is well trained, you want to also be sure that by the time you evaluate it, it gives a good performance. So why do we have to validate models, right? Model validation is critical for evaluating model generalization. It also helps to prevent overfitting because a model performs well on training data but poorly on test data. If that happens, right, that leads to overfitting. Overfitting is when a model performs well on training data but it performs poorly on test data. So for you to have a reliable model, then it should do well on both training data and test data. Another reason why we validate models is to provide a reliable estimate of model performance before deployment. So let's go ahead. So here we are focusing on train test split as well as cross validation. So those are the two ways we are looking at for validation and tuning. So for the train test split, the concept is such that we divide the data set into two mutually exclusive subsets. I think the word mutually exclusive is really very important in this case because you don't want, I think 4 videos from now, we'll be talking about data leakage. So when maybe the test set spills into the train set or train set spills into the test set, that's when you have something like data leakage. So the training, so you have to ensure that the training and test data sets are actually exclusive subsets of the overall data set. So the training set is used to train the model, like I've been saying, and the test set is used to evaluate the trained model, right? So the typical split ratio is 80% training, 20% testing, or 70% training and 30% testing. So those are like the typical in most situations. And of course, we can actually look at this in deeper levels, right? Depending on the largeness of the data you're working with. So in some cases, there may be other considerations. All right. So of course, a couple of times I've also thought about a kind of 67-33, 67% training and 33% testing. So it all depends. But this 80-20 and 70-30 are the most popular, the most common. So the advantages of the train and test set, the train test split is that it's simple to implement and it is very fast. It is fast and efficient. For disadvantages, right? It can have high variance in performance due to random split. The split is random. So it's like, yeah, because it's like the idea of random sampling in statistics. So you're just taking 80, if you're for the 80% training sets, right? You're just taking 80% randomly to be sure that you don't follow a particular pattern that leads to some kind of trouble. Then there's also a risk of biased evaluation if the split is not representative. So since the split is random, sometimes you may be sure that what you take as training set is not representative enough. And of course, thankfully, that's why we have things like tuning, hyperparameter tuning, and all of these things as we are going to see in the next video. So let's look at a code example for train tests. So of course, as usual, you need of course, scikit-learn is a key library for machine learning. So NumPy for numerical analysis, pandas for data manipulation, data analysis, data cleaning, and all of that. Now, machine learning, you have scikit-learn, of course, for data visualization, the top two will be Matplotlib and Seaborn. So from scikit-learn dataset, we are using the iris dataset. Now, we use the iris a whole lot of time because it's very just for educational purposes. In very serious situations, the iris dataset is too simple, but it's very good as a dataset to teach some of these machine learning concepts. So, of course, you need the train test split function. Then, in this case, we are trying to do this train test split with a random forest classifier. So we are doing a classification algorithm. Then we need the accuracy score for some measurement. So in line 7, we load the iris data. Then we do the split in line 10, X train, X test, and all that, the usual thing we do. And then we have the test size is 0.2, meaning that the train size is 0.8. That's 80% for training and 20% for testing. Then to train the model, just have model equals random forest classifier, random underscore state equals 42. The model dot fit is X train, Y train, like that. Then once the model is trained, then you can now do the testing, right? So you evaluate on test set. So you have predicted value of Y is now model.predict X test. Then you get the accuracy to see what happens right there. So I just run that and okay, we have the result now. So the accuracy of the train test split is 0.9. So the accuracy of the train test split is 0.9. That's 90% accuracy, not a bad one at all. It can actually be better. So that's talking about train test split. So the other way of validating your model is what is called cross validation, and it's really it has a huge advantage over train test. It all depends on what we're doing. So for cross validation, CV for short, rather than a single split, what we did before was just a single split, 80-20, and that's it. Cross validation actually divides the data into multiple subsets, which are called folds. And that is why I talk about a k-fold cross validation. So it divides the data into multiple sets or folds and rotates the validation set to ensure every sample is tested. So this way, you are ensuring a more thorough split, so to speak. So types of cross validation, you have k-fold cross validation. Here, data is split into k equal folds. So if k is 3, right? If you do a three-fold cross validation, then the data is split into 3 equal folds. Each fold is used as the validation set once. Then you can have a stratified k-fold CV. This maintains class proportions in equal fold, and this is used for classification. Then you can have leave one out CV, that's leave one out cross validation, that's LOOCV. Extreme case of k-fold, where k is equal to number of samples. So in that case, it's more like every sample you have is actually a fold. That can be a whole lot. You can be sure of that. Then you have repeated k-fold cross validation that repeats the k-fold process multiple times with different splits. So now, talking about k-fold cross validation, so focus on the first one now. So the workflow is such that you split the dataset into k equal parts of folds. Then for each of the k iterations, you move over each part. So you use one fold as the validation set, and then you use the remaining k minus one fold. So if you have like 5 iterations, so you use one as validation set and use the remaining 4 folds as the training set. Then you go ahead and train and evaluate the model. So if you have 5 folds, five folds, right? So you train your model with 4 folds, and then you test the model with one of the folds. Then at the end of the day, you average the performance metrics across the folds. So talking about the advantages now, it is more stable and reliable performance. It is a more stable and reliable performance estimate compared to the the train test split. Then it uses more data for training than simple train or test split. So more data for training. Then it reduces risk of overfitting to a specific data split. right? So this disadvantages will include that it is more computationally intensive, having like K training processes. So the more the training processes you have, the more computational power is used. Then it is still susceptible to data leakage if preprocessing is done before splitting. So you want to do your preprocessing after splitting, not before splitting. Then code example, we are taking let's do a five-fold cross validation. That means K in this case is equal to 5. So the data sets are partitioned into 5 parts. And, as usual, for model selection, we have the cross validation score. That's a metric we'll be using here. Then we have the ensemble you're using is the random forest classifier, which of course we saw to be better than decision tree, because a random forest is composed of many trees aggregated and averaged out. So then we have the data set, of course, iris as we've been using. Then we have we load the data set, say XY is load iris, return XY true. Then initialize the model. So the model is random forest classifier, random underscore state equals 42. That's to guarantee that you get the same thing each time you run, because without that, each time you run, you're going to get a different result, and that can be really frustrating. So you want to be sure that the result does not change. Then we can then perform the five-fold cross validation. So the cross validation scores can now be obtained by using the cross-val score function. So cross underscore val underscore score. Then the model, that's the random classifier model we're using, with the x. These are the features, and y the target. The cross validation is equal to 5. So because you have five folds, and then the scoring is based on accuracy. So the output results. So you can upload the result by printing the cross validation scores. That's the CV scores. Then you can now also print the average five-fold CV. That's the average of the CV scores. So that's a more rigorous process than simple test split, and then you can be sure it will be more reliable. But because of the data set we are working with is very straightforward, it's very simple. So you won't be surprised if the results are the same or almost the same. Okay, for train test split, right, we got 0.9. And so even with this data set, you still have five-fold cross validation better than that, because the cross validation scores across the five sets, we have 0.96 something, 0.966, 0.933, 0.966, then 1 again. And the average, if you average it all out, you have to two decimal places, that's like 0.97, whereas the other time we got 0.90. So you see, even on this very straightforward data set, five-fold, K-fold cross-validation gives better performance than simple split, a simple train test split. Okay, so what we did there was just was the K-fold cross validation. How about if we consider the second type of validation? If you remember from the table, we have K-fold cross validation. We also have stratified K-fold cross validation. So can we see that? So with stratified K-fold, which preserves class balance, then it's so here for the model selection, you need the stratified K-fold and the cross-val score, and then you just have stratified five-fold CV. So SKF is stratified K-fold. Then you have five splits. Any split is five. Shuffle through random for the two. Of course, we know what that does. It maintains the results. So things the result doesn't keep changing. So the CV score in this case, now we are using another model entirely. So the CV scores will now be cross-val score model X, comma Y. CV is SKF, and then the scoring is based on accuracy. So let's print this now and see if it's better. Okay, all right. So here for the 5K five-fold cross validation, we had 0.97 to two decimal places. Here we have 0.95. So the 5K validation, the 5K five-fold cross validation actually performs slightly better, than the stratified K-fold. So what happens most times is when you do a machine learning task, you want to do different metrics to have so you can actually be very sure what your model performs like. So let's look at a comparison table. So we want to compare between um, f- um, train test split and k-fold cross validation. Talking about simplicity, train test split is straight is of course simpler, and k-fold is more complex. Bias in evaluation, there's high bias in evaluation because you have just one test set. But for k-fold, it is low because it is averaged over the number of folds you choose over k-folds. The variance in results is high in train test split, whereas it is lower because of averaging in k-fold cross validation. Computation time is low for train test split, of course, for obvious reasons, whereas it's higher because you have k iterations for k-fold cross validation. Data utilization is partial for train test split, but k-fold cross validation, you have full data utilization because each point is used once as a test. Then reproducibility, this depends on seed. And then for seed is like that 42, that random state you keep seeing, right? 42. So if you remove that thing, right? So it will be difficult to reproduce because each time you run the model, you get a different result. So that's why. So it depends on seed in short for reproducibility. K-fold cross validation depends on folds plus seed. So now beyond the seed, now you also want to talk about the partitions, the number of folds you have for cross validation. So let's look at some best practices for model validation. So first of all, we have to choose K carefully, right? So common choices of K would be 5 or 10. So those are common choices for K. You can also use stratification for classification problems to maintain class balance. So the stratified thing we used the other time. In fact, despite the fact that the five-fold cross-validation performed better than the stratified k-fold. The stratified one may even be more reliable, though that one is giving a better result, so to speak. But the stratification thing may be more dependable because it maintains class balance. And you can also pre-process within cross-validation loops. So to avoid data leakage, like in scaling and encoding, so you have to pre-process within the cross-validation loop to avoid data leakage. Then use scoring metrics appropriate for task. So, just like you already know, for classification tasks, they have their own metrics like accuracy, like precision, like recall, and so on. Whereas when you come to regression algorithms, then you begin to talk about things like mean average score, mean square error, root mean square error, and of course R squared. So you want to use the appropriate metric for each task. So accuracy for classification, that's top, and root mean squared error for regression, and so on and so forth. Then you also want to use grid search CV or randomized search CV. That's grid search cross validation or randomized search cross validation. This will help you to combine model selection with cross validation. Okay, I mean, as a snippet, because we're going to talk about hyperparameter tuning in a subsequent video, but as a foretaste of that, we can look at hyperparameter tuning with cross validation. So in this case, from scikit-learn.model selection, we can import the grid search cross validation, and then the parameter grid. You have the number of estimators. So you try for 50, 100, 150 for maximum depth. None means no end to the depth. And then, I mean, when we talk about depth, right? I think the earliest example we had about depth is when we're talking about decision trees. So if you say that a tree, the depth of a tree is 2, so you don't have more than if the depth is 3, right, you don't have more than 3. You don't branch down more than 3. That's the idea of depth. So when we say none, it means it can go as far as possible. Then you have that comma 3, comma 5. So 50 estimators with no depth, with any amount of depth, 100 estimators with 3 depths, and 150 with 5 maximum depth. Then for grid search now, so we have brought the grid search. So the grid search, this is just a variable name, but the actual thing is this function grid search CV into estimator. We take the whatever model we are using, then parameter grid, that's parameter grid. Cross validation is equal to 5. So that means we have 5 folds, and the scoring is based on the accuracy. So the accuracy tells us the performance. Then we can now fit the model. So grid search dot fit XY. Then we now do the now try to get the estimate. So grid search best parameters, grid search best score. So I run that, and then it takes a bit of time. Of course, it's tuning that is taking place, and it is taking place across these values. So here, the maximum depth. So if you look at it, so we are choosing from these possibilities, right? So the final answer is that the best estimator will be 50, right? At limitless number of depths. and that gives a best cross-validation score of 0.97, right? So that works. In conclusion, both train test split and k-fold cross-validation are essential tools for evaluating machine learning models. So use train test split for quick prototyping. So if you want to do a quick job, train test is what you have. But you can use k-fold cross-validation for robust and reliable model evaluation, especially before deployment or during hyperparameter tuning. So if you want more reliable results, so k-fold cross-validation does the job. So thanks for listening. Let me know how helpful this video is for you. And if there's something you like want to try out, feel free to let me know. If you have subscribed already, thank you so much. If you haven't, please go ahead and subscribe and be sure to hit the notification bell so you can always get alerted each time a new video is released. On my channel now, you can be a member at bronze, silver, or gold level, and those come with different perks like getting PDF copies of my math lectures on request, or having a bad display beside your name, or even having some videos exclusively for you, or get to see some videos way before other people see the videos. And of course, you can even have one-on-one consultations with me depending on the membership class you belong to. But of course, if all you do is subscribe, you're good. I mean, you still have most of the videos at your beck and call. So um, be sure to share and like also so that more people can have access to the great content I have going on here. Till I come your way again, keep doing data right. Bye.